Welcome back. Based on some feedback that I've received earlier as well as after the class yesterday, there was some feedback. So we're going to change, how we're doing this module a little bit, and I'll talk about what change we are going to do. Uh, okay, so what I'm basically doing is I'm taking things from what I was going to do today and what I was going to do in the next class, and I'm putting them together as a different section. And in a moment you will see what I mean. Okay, and again I'm kind of doing this on camera because people will have access to lecture notes, the raw lecture notes as well as the annotated lecture notes. So, in order to avoid any confusion, this is something that would hopefully be useful. So, and I'll talk about what exactly I mean. Okay. So, what we have been doing so far in this course is we have talked about a particular problem or a particular topic. We have tried to introduce some of the fundamentals of the topic. How do we approach various problem solving, went through overall derivation, and then finally took up problems or examples that we then tried to solve. One of the feedback was that when we are listening in the class, when we go back, when we look at the material, it seems like we have understood the material, but when we actually sit down and try solving problems, we are facing some difficulties. Okay. So, one thing that you need to do in order to address those difficulties is your assignments and your lecture notes are not fully sufficient. If you want to learn more, learn better, you need to look at the books. Okay. Although Froment and Bischoff is a more appropriate textbook for a PG level course, uh, Davis and Davis is a more approachable book, for lack of better words. So, therefore, what I've tried to do is take examples from Davis and Davis, including a couple of solved examples also have solved. Okay. So, what you want to do is at the start of each module, I talk about what chapters from the textbooks you need to look at. Okay. So, please go and read those chapters, and more importantly solve the solved problems or the exercise problems at the end of the chapter. The assignments that you have are not very different from the problems that are solved problems or exercise problems in the books. In some cases, probably in more than 2/3 of the cases, those are problems from your textbook itself. I have not created a different problems, or I have not taken it from a hidden textbook or anything like that. Those are problems from these two books itself. So, go ahead and resolve the solved problems over there, right? Look at the solution, keep the book away, and then solve the problem yourself. Wherever you are stuck, for half a minute, for 20 seconds, quickly revise how they have solved it, close the book, continue solving the problem. Okay, that's the way you would want to do if you are really struggling. If you are able to handle those problems, definitely you can go ahead and solve those problems yourself. Okay. So, that is something that you need to do. The expected effort in the every week we are meeting four times in 4 50-minute sessions. So, what change we are going to do is, we were talking about fundamentals. Okay. What we will now talk about, rather than talking about fundamentals and the derivations and what do those expressions mean and so on, we will try to talk about how do you approach solving problems. Okay. So, I have taken out, you might have seen that I have taken out 1 or 2 slides from what I would have talked about today and in the next lecture, and I have put them together. So, rather than deriving something or rather than talking about the fundamentals of how that particular approach is used, I am going to talk about how you will use those concepts in order to solve problems. Okay, so that's the change that I have done in today's lecture. So hopefully that will help you understand the material a little bit better. In the previous lecture, what we did is we did a thought exercise where we said there were a few red balls and a few blue balls. Okay. Now, if or red molecules and blue molecules, and now if you allow them to diffuse, the red molecules will net move in this direction, the blue molecules will net move in the opposite direction. Okay. What governs the movement? The movement is given by the molar flux because of diffusion or mass flux because of diffusion. This is the flux of kth species because of diffusion. This is in terms of moles per meter square second or moles per centimeter square second. This is in terms of kg per meter square second. Okay. They are related to each other just by the molecular weight. Okay. Fick's law, this is the law that you can use so the Fick's law basically says Jk okay, this is the first law. Fick's second law says that this is the first law, second law. Okay. Immediately you will notice that the second law is nothing but the approximation from the overall thing that we have derived, that is dou Ck by dou T plus if there is no reaction, if there is no convection, okay, and diffusivity remains constant or does not change with location, then you will basically get the Fick's second law. Okay. So, Fick's second law now is not considered as really law, or not now is not considered. We won't consider it as a law that we will use at all. Okay. Fick's first law was derived in case of binary systems. Okay. It's applicable, Fick's law is applicable for binary and for dilute systems. Okay. And I am going to replace this by dKm, where dKm is diffusivity of species K in a mixture. Okay, so Fick's second law is a special case of the species balance of module 1, special case where no reaction is taking place and there is no convection in the system. Okay. So, this is all I have to talk about the Fick's law. Okay. When it comes to the overall behavior of the system, what we talked about was, let us think of a school bus. going with 10 standard kids and first standard kids, right. So, this is what we talked about. The net motion of the bus is, if we were able to track each and individual kid, okay, we will get what is known as the molecular velocity UK, okay. Ck multiplied by UK is the net molecular flux, okay. Unfortunately, for most practical cases, we cannot measure this. Okay. The velocity that you measure, okay, is a mass average velocity. All that you have been studying about from pretty much from 4th grade, 3rd grade, 4th grade, that this is the velocity that you can measure. That velocity, when it comes to fluids that you can measure is a mass average velocity. So, what you measure is summation of omega k UK, okay, and the difference between the two gives you basically the overall flux. Okay. So, this is what I ended, I think, the previous lecture with. Okay. So, this is where the overall idea of JK comes from. Okay. All of this you can forget, does not matter, this is for your understanding. What can you use from this? The one main thing that you can use from this is, because of this, if you add up Jk over all species, the Jk bar over all species, they will become 0. Okay. This you can also get from your overall species balance. If you add up overall species balance, the left hand side will become the continuity equation, the right hand side has to become 0. Okay. The reaction term added over all the species will become 0. So, also the diffusivity term. Okay. So, summation of del dot Jk will be equal to 0, okay, and that becomes 0 when del dot Jk bar will become 0, that becomes 0 when Jk bar are all 0 summed over. Okay. That is the only thing that you need to know with respect to all of that derivation. So, you know, there's all these children moving around, running around in the bus and all that. If it makes that confusing for you to use, you don't need to really use that. The only thing you might need sometimes is this. The other thing, the next thing that you will need is, what is Stephen Maxwell's? Okay. So, Stephen Maxwell's law captures the diffusion behavior in the overall system. Okay. That is derived basically from probabilistics argument, statistical mechanics. Okay. And this turns out that, so delta x a, again you do not need to write it, delta x a is summation okay, or let us say DAB is diffusivity of A, how A diffuses in a medium full of B. Diffusivity dBA is how B diffuses in a medium full of A. Okay. This can be obtained by kinetic theory of gases for gases. Okay. So there are a couple of relations that you can use in order to obtain this. Okay. So for gases, you can use something called Chapman-Ensog correlation. Okay. For liquids, you can use the Stokes-Einstein's correlation. For gases, you remember yesterday we talked about diffusivity is dependent on temperature. Okay. So for gases, the diffusivity is proportional to the temperature to the power 1.5 for gases. Okay. It is also dependent on the molecular weights of the diffusing species. Okay. Larger the molecular weight, lower is the diffusivity, smaller the molecular weight, larger is the diffusivity. Okay. And it is proportional to T to the power 1 and mu to the power minus 1 in liquids. Okay. Gases, the order of magnitude okay. Again, as engineers, it's important for you to know order of magnitudes of this. So if you are looking at gases and diffusion in gases and you see that the diffusivity is say 10 to the power minus 2, minus 3, let the temperature, may ensure that the temperature is really high. Again, 10 to the power minus 3 is quite unlikely. Okay. You will then know that there is some mistake somewhere, either in the data or in our interpretation of the data. Okay. So these are the things that you can use. Stephen Maxwell's, for the most part, you won't really need. Okay. But from Stephen Maxwell's, what we can use is, if it is a binary mixture, what you are going to have is that for binary, okay. So CDAB, you can take it over here. Okay. If you do the same thing you will get this. Okay. So if you add them up, you will get them to be 0. This is what you have learnt as equimolar counter diffusion. Okay. And if it is binary, okay, this particular guy, okay, essentially is minus JA. Okay. So what can we use from all of this? What we can use from all of this, and the other thing that you can do, because you can add this up, okay, XA equal to 1 minus XB, or XB is 1 minus XA. So del XB is minus del XA. Okay. Again, I am not doing the derivation, I will do the derivation in the next class. So if you are not understanding the derivation, that is actually fine, no problem. What can you use? What you can use, if you ever need multi-component diffusion, you use this. Because of binary assumption, but not binary assumption, because we have only considered binary case, adding the two Stephen Maxwell's expressions up, we have obtained the equimolar counter diffusion using the idea that Xa equal to 1 minus Xb, we can derive DAB equal to DBA. Okay. So, the diffusivity of A in a C of B is exactly equal to the diffusivity of a B molecule in C of A. Okay. So, molecular diffusivity DAB equal to DBA. Okay. For binary mixtures, Fickian is exactly equal to Stephen. There is no approximation in Fickian when it comes to binary mixtures. When it comes to multi-component, Fickian is equal to Stephen if the medium is very dilute mixture. Okay. So, for example, solution of A plus B plus C in water, when we are talking about 0.1 molar, 0.5 molar and so on. Okay. There is hardly any approximation in Fickian. Okay. And you can use it. Okay. The other thing that we will come to, will not come to that today, but other thing that we will come to is something called DAM. Okay. So, let us say you have a mixture of A plus B plus C plus D plus E, say 5 components. Okay. You have DAB, DAC, DAD, DAE. Likewise, you will have DBBA, DBC, DBD, DBE and so on. Okay. So, from all of these, and of course, DAB equal to DBA, DAC equal to DCA, DBC equal to DCB, all of those we have we have skipped the derivation, but it can easily be derived. Okay. So, from all of these you can compute DAM. Okay. Once you compute DAM, you can use your Fick's law for 90% of the cases. Okay. You will not be able to use Fick's law in a few cases, but in 90% of the cases you will be able to use Fick's law if you use a mixture average diffusivity. Okay. So, again to summarize, overall balance, Actually, I won't even put this because for the most part you are not, I don't think you are going to use that. Okay. So, these are the things that you are going to use, that is all. Okay. So, you do not need to necessarily write down everything on that slide right now, but at least write down in the books that the summarized slide is the one that is summarized. Okay. Okay. Examples that we are going to use, we will do that in the next class. So, next class will be tutorial. So, we will do 2 examples. We will do one example where we are going to do some of the computations where we will use the summary from this slide, and the second example is the one that we will use for looking at analyzing external diffusion. Okay. For external diffusion, we will go a few slides earlier, and I am going to ask you to recall this particular picture. Okay. So, we have some concentration 0.85 in the bulk phase, we have some concentration 0.81 on the surface of the catalyst. Okay. The reason why it is 0.81 is because there is reaction taking place. Okay. And again, I am using the term reaction in extremely broad way. The reaction could be actual reaction taking place on the surface, it could be reaction taking place inside the pore, it may not be reaction, it might just be adsorption taking place inside the pore, or it can be something else, maybe Harry Potter has created some wormhole and then the molecule goes in and it goes through the wormhole and comes out somewhere else. As far as we are talking about external diffusion, what actually happens or how does the species A disappear, that does not matter. What matters is, do we know what is the rate of disappearance of that species, that is all that matters. Okay. Okay. So, for the so all of this, in these cases we consider a boundary layer, all of this, and then I talked about delta yesterday, that is the film thickness, and then I talked about characteristic length. All of that was towards the derivation. Okay. What are we going to use? What are we going to use is, on the surface the concentration is CAS, in the bulk concentration is CAB. On the surface where the reaction takes place, concentration is CAS, in the bulk concentration is CAB. Okay. On the surface where the reaction takes place, concentration is CAS, far away from the surface concentration is CAB. Okay. Rate of diffusion is proportional to the concentration difference. Okay. Note that there is no reaction taking place, so therefore we can approximate the the overall Fick's law as just the concentration difference divided by delta. Okay. And as I said in the previous class, the delta will be replaced by some kind of characteristic length. All of that we will incorporate into a term called mass transfer coefficient. Okay. So, rate of diffusion is proportional to CAB minus CAS. Okay. Or sorry, Okay, why flux? Yeah, the derivation comes through the Fick's law. Okay, so flux is in terms of okay. Remember what we said yesterday as well as what we said in the beginning of the previous module, concentrations. Okay. So, therefore, the units of kCa are on meter square surface. Okay. The units of kCa might be meters per second, but always think of meters per second in terms of meter cube fluid per meter square surface. Okay. For this module it will not matter at all, in module number 9 this will matter. So, just remember that, keep it at the back of your mind, so that in module 9 when we revisit this concept, it is not something that you are again coming to know of suddenly. Okay. So, again these are all equivalent, whether it is based on concentration difference, its mass transfer coefficient based on concentration, if it is based on mole fractions, its concentration, its mass transfer, it's a mass transfer coefficient based on mole fraction, if it is based on partial pressure, mass transfer coefficient based on partial pressure. Okay. We will use this most commonly, okay, for this particular course, but again doesn't matter, all of these are equivalent. Okay. They have form of k multiplied by the driving force, okay, and therefore this is also called a linear driving force model. Okay. Then the question is, where do you obtain this k from? We obtain this k from Sherwood-Rumber relationships. So, let us think about the case that we talked about a few days back, not few days back, in the previous class. The concentration over here is 0.81, concentration in the bulk 0.85. Okay. Okay. What we need to know is what is the rate of disappearance of A on the surface. Okay. Let us assume that A disappears okay. If we look at this surface, accumulation equal to rate in minus rate out plus reaction. Okay. Steady state, so accumulation is 0. Okay. In minus out is our JA. Okay. So, let us write R dash, right. Okay, the surface does not have a volume, okay, that is why we are taking R dash. Okay. So, we had 0 equal to JA multiplied by area area get cancelled. Okay, let us say the reaction rate that you had was in terms of moles per unit volume of the catalyst. If that was the case, we will have let us say it was given per unit mass of the catalyst. Oops. Okay. Whatever it is, does not matter, as long as we are looking at that particular interface and what is happening. Okay. In your textbook, you will basically have this particular thing only. Okay. But if you go to again later chapters, that particular assumption is relaxed. So, why keep it for later? Okay. So, let us look at this particular guy itself with a first order reaction. If we were to substitute these, you will get 0 equal to Ca where? Ca at the surface. Why? Because reaction is not taking place over here, reaction is taking place on the surface itself. Okay. So, if we were to do this, we will get okay, and rate of reaction is nothing but K dash multiplied by this. Okay. I have just put an S over there as we have just discussed half a minute ago. That is essentially this derivation. Okay. Just a little bit of a difference, sign conventions in the opposite direction of mass. Okay. But you do not have to worry about it, as long as just think you are sitting on that surface and think about whether A is coming or whether A is going. If A is coming, then it is in minus out. If A is going, then it is out, negative in minus out, that is all. Okay. So, A is coming and is whatever net is coming is getting reacted away. Okay. So, just because of the sign conventions, these things are written like this, but otherwise you will get the same guy. Okay. This is a problem that we will do, one of the problems that we will solve next class. What if it is this? How will your analysis change? It will become a quadratic equation. Okay. What I want you to do, you have so many days, right? This is there for your quiz. Okay. In addition to working on modules 1 to 4, also work on trying to solve this problem. Okay. If you break down the problem into the concepts, mass transfer to the pellet is one concept, reaction on the pellet is another concept. Okay. Because accumulation is 0 at steady state. Okay, there is another reason why accumulation is 0. Accumulation is 0 because the surface does not have any volume. So, that is why you remember accumulation is d by dt multiplied by the amount into the volume of the control volume. So, surface might have infinite area, but 0 volume. Okay. So, that is the other reason, but leave that aside. So, 0 equal to in minus out plus reaction. Okay. In minus out is by diffusion, reaction might be first order, fifth order, nth order, 75th order, Langmuir, Hinshelwood, does not matter. Equate the two, solve the overall equation, try to do it yourself. Okay. It is a solved problem in Froment and Bischoff. You are stuck, talk to your friends. Collectively you are stuck, expand your friends network. Entire class is stuck, open Froment and Bischoff. Okay. It is a solved problem. Okay. There is no excuse for you to not be able to come prepared for the tutorial with this. Okay. Again, I am not saying that it is easy. All I am saying is that if you put in effort, it is doable. Okay. That is one thing that I wanted to come prepared with. Ka, I will just put Ka. Okay. How do we get values? We get values from mass transfer coefficient correlations. Okay. This could be Sherwood number correlations or the JD factors, the Chilton-Colburn factors. Okay. Expression for Sherwood number I had given you earlier. where L is L characteristic. What K? K of species A. What D? DAM. Okay. There is no real derivation that we are going to go over, there is nothing really that we are going to go over. If it is a single particle, use this correlation. If it is a flow in foams, use this correlation. If it is not a single particle, but it is a bed of spheres, use this correlation, where Nusselt number is given by this, Sherwood number is given by this, Schmidt number is given by this, JD is given by this, and so on. Okay. It is primarily a matter of finding the right expression, substituting the values, getting your K, putting that K in the right expression, solving the problem. Okay. So, this is the other summary slide. Okay. Module 5, something that I absolutely hate doing, module 5A. Summary number 1 is this, summary number 2 is this. Okay. That is essentially what all of the derivations and all of the discussions for module 5A summarizes to. Okay. We will use this and solve problems in the next class, and thereafter we will revise, quickly go over the derivation again. Okay. Why we will go over the derivation again is because you need to understand how we have derived things in order to use them in the right way. Okay. I find that even when I was a student, it took me maybe as a PhD student maybe 6 weeks or so to actually get the units right, get the parameters right, get, oh, it is meter square particle, meter square reactor bed, meter square what exactly is it, all of those, meter square its outer surface, meter square its inner surface, how do I get inner surface, all of those questions are there, and you get totally stumped if you are only going to use those equations blindly. Okay. So, we are going to use the equations more or less blindly in the next tutorial class. After the tutorial, we will spend half a lecture to go over the derivation all over again, so that the concepts get reinforced. Next class, how to solve, we will try to reinforce by using tutorial. Thereafter, the concept we will try to reinforce. So, I have just based on your feedback tried to change the nature of the lecture a little bit, so that we solve the problem and then go over the derivations all over again. Okay. All right.